Hello everyone, my name is Clement Sakura, and today I'll be talking about the multi-agent routing value iteration network, also known as Marvin. There's little question these days that self-driving cars are going to be essential in our society in the future, with all the advancements and discoveries that are being made. However, these vehicles often require high-definition maps of a region that they're expected to work in, and these maps often require periodic updates. This motivates the need for a system that is able to autonomously map a region and coordinate an increasingly large fleet of vehicles in an efficient, scalable, and adaptable manner. The idea of an agent or fleet coordination system is not a new one. A similar idea has been explored in the case of the traveling salesman problem. In this problem, we have a series of points on a plane, and the idea is for the agent or salesman to visit all of the points exactly once in the most efficient manner possible, and then return to their original starting positions. The vehicle routing problem is a natural extension to this with multiple agents. Given a set number of agents, which all start from the same initial starting city, all are expected to visit some subset of points, so that after all agents have finished, every point has been visited exactly once. Bringing this back to mapping, each node could be a representation of the cities that need to be visited, or even the individual streets. There has been a considerable amount of work into TSP or VRP iterative solvers, which can relatively consistently determine the optimal solution to a given problem, as seen in the case of Concord or LPH3. In the deep learning field, a few steps have been made towards developing a deep learning solver that can be considered more adaptable than iterative solvers, such as in the attention model, or AM, and a code-attend navigate, or EAM. There's also been some work into exploration-based architectures, as seen in the work of the value iteration networks. However, these kind of solutions each run into their own set of issues when running in a more realistic setting. When we consider real map graphs, it becomes evident that they can't be represented by 2D coordinates on a plane, and the complex connections can only really be represented by using a sparse map graph. Deep learning solutions usually require that the nodes be fully encoded just using their relative 2D coordinates, and therefore struggle in this map environment. Furthermore, when we are sending out our vehicles in practice, they have to contend with unknown traffic conditions, random mapping failures, and other changes in the environment. Iterative solvers tend to be too slow to adapt the trajectories of an entire fleet online, and also struggle to efficiently integrate stochasticity into their model, meaning that they're not well equipped to work in a realistic domain. Of course, in the field of real-time adaptation, learned differentiable communication has recently provided a means to generate deep learning models that can communicate information between other deep learning agents in a swarm. Similarly, novel methods for properly encoding a graph environment have been developed that could allow us to operate on a graph directly. However, in practice, mapping tasks tend to be conducted in a somewhat inefficient manner. What tends to happen is an initial trajectory is calculated using an iterative solver offline, and the fleet of vehicles is sent out to perform the mapping task, as seen in the mapping attempt 1. After they return, we determine which streets had mapping failures, and we send out the vehicles again, as seen in mapping attempt 2 and 3. This process is repeated until every street has been completely mapped, which, as you can patently see, isn't necessarily the most efficient practice due to the lack of any real-time adaptation. As a result, we approach this problem in the following proposed architecture. We extract node information from the map graph, encode that information, and then send these node encodings to our novel conceptualization of the value iteration module. This module iteratively exchanges information between each of the nodes and allows for complex planning to occur in a distributed manner. Finally, the communication module exchanges node information between each of the agents and allows relevant discoveries to be made and shared. The final output is also returned to the map graph in the form of a per node value function. Now, getting into the specifics of our model, our value iteration module takes in as an input both the encoded node features and the adjacency matrix, represented as a dense normalized distance matrix, which can be found using the Floyd-Warshall algorithm. At each node, information vectors from every other node are combined using an attention mechanism and then passed to an LSTM module, which acts as the memory unit for each node and helps produce a new set of node features. These are added to their original features as a residual, and this process is repeated over several iterations. At the very last iteration, we decode the node features into a value function at each node. After masking out the nodes that have been already completely mapped, we convert our value function into a probability distribution of traveling to that node in the next step. Here, we visualize the multi-agent routing value iteration network's internal action value function as an ever-evolving heat map. On the left, you can see agent 1, and on the right, you can see agent 2.
The yellow and green clouds represent the heat map values and therefore which region the agent is most likely to visit in its next step. The red and blue dots represent the vehicle's positions when making these decisions. The agents generally alternate between focusing on specific regions to systematically map and more generally exploring new untouched areas.
The final set of node encodings are also decoded into a communication vector. This set of vectors is broadcasted to all other agents and saved into a memory unit. When taking the next step, each agent combines the communication vectors of all other agents using a self-attention mechanism on a per-node basis to produce a new set of node features that we concatenate on the input node features. Now, we will illustrate how we construct our proposed mapping simulator benchmark and how we generate our novel, strongly connected map graph dataset. We begin with taking the map graphs of 15 international cities and converting them to weighted adjacency matrices. The nodes represent the streets that need to be visited, and the weights of each edge represent the expected time required to travel from one road directly to an adjacent road. Next, we randomly sample these graphs for strongly connected smaller subgraphs between 10 and 25 nodes in size. We were able to generate over 23,000 graphs using this practice. Instead of relying on the 2D coordinates, as is done in the traveling salesman problem or the vehicle routing problem, we make no such assumption and only provide our model with the weighted adjacency matrix. Once we have all the sampled subgraphs, we then stochastically add realistic challenges. Firstly, we simulate what realistic traffic should naturally look like, and then use these simulations to assign each street in the graph a congestion value. As this value increases, the time required for a vehicle to traverse that street shall also increase. This congestion value is initially unknown to all the vehicles, and only becomes known after the vehicle has visited the street, thereby mimicking unknown traffic conditions. We similarly simulate the possibility of there being mapping failures when each vehicle attempts to visit a street. This could be caused by unforeseen occlusions, hardware malfunctions, or other unpredictable issues. The way we simulate this is by assigning each street a difficulty index. The index is uniformly sampled from 1 to 3 and represents how many passes are required before the mapping task can be considered complete. As this index is unknown to all the vehicles, it is tantamount to each street having a random probability of needing to be revisited. We tested our model using two main training techniques. The first we will discuss is imitation learning. In order to find the ground truth basis, we first transform the graph by duplicating nodes according to how many passes are required before the mapping task is complete, and alter the edge weighting to reflect the unknown traffic conditions. This allows us to use a traditional VRP solver to find the optimal traversal path, since we no longer have unknown stochastic states in our graph that require online updates. In our case, we use the solution provided to us by the LKH3 iterative solver as our ground truth, and train using teacher forcing, where the agent unrolls according to the ground truth path. We also train using reinforcement learning in order to verify the generalizability of our model. We set the negative total traversal cost to be a reward function, and using episodic rewards, we train using vanilla policy gradients. We now present the primary findings of our study in the form of the average cost of a traversal. It should be noted that for all deep learning methods, we only train using graphs of 25 or fewer nodes, and only with 2 agents at a time. Cost in this context represents the total traversal cost, gap represents the percent gap between this method and the Oracle ground truth optimal, and runtime is simply the runtime of that algorithm in milliseconds. Firstly, we find that our model is generally able to outperform solutions provided by the state-of-the-art, represented by LKH3, and also outperforms a naive greedy search by a considerable amount when enrolled with a single agent. Scaling now to 5 agents with graphs 4 times as many nodes, we see a similar trend where our model outperforms the state-of-the-art solvers and is able to get the closest performance to the true optimal out of the basic alternatives. Comparing to other deep learning architectures, this pattern is repeated. We show that our particular architecture, when compared to other generic graph-based alternatives, such as the graph attention networks and the generalized value iteration network, result in the best performance in the single-agent context. When it comes to other deep learning TSP solvers, we find that their reliance on 2D coordinates and their inability to adapt their traversals hampers their overall performance. Qualitatively, we also observe that they ran into significant issues when attempting to deal with the multiple traversal aspect of our simulated benchmark, and as such failed to provide adequate traversals. Due to their inability to adapt and communicate, we only consider them in the single agent setting. Finally, this trend is again maintained even when the agents are scaled to even larger graphs and increased number of agents. In order to reach a fair comparison, we equip each of the alternative deep learning models, as seen here, with our communication model, and therefore only evaluate the path planning abilities of the internal architectures. We'd like to note how our method, when trained with imitation learning, actually scales much better relative to the number of nodes than when trained with reinforcement learning. Here we qualitatively compare the mapping process of our method to that of another competitor architecture, specifically that of the generalized value iteration network. We find that our model results in a more thorough mapping process where we prioritize filling in all the regions completely over exploration. The competitor network seems to prioritize exploration over completeness, and as such takes noticeably longer to complete the mapping task. Due to the mapping failures that can occur, the lack of information about where these mapping failures are a priority results in this task being a very non-trivial one in itself. We similarly compared the qualitative performance of agents trained with reinforcement learning to agents trained with imitation learning. When scaling to much larger graphs, we found that imitation learning agents are able to prioritize exploration while simultaneously ensuring that revisiting previously visited regions is done in an efficient manner. One question we sought to tackle in this work was to determine how adding more agents affected the performance of the model. Here, we can see that as we add more agents, the total cost of performing the mapping task only marginally increases, meaning that the mean cost per agent decreases nicely with the number of agents used. For the sake of generalization, we also evaluate our model on a traditional TSP environment. In this case, we train our architecture using the methodology described in the attention model, AM, and compare our performance on the set of 20,000 randomly generated graphs. In its most basic form, we find that our model achieves relatively decent performance when compared to other deep learning iterative solvers, considering that it is 3 orders of magnitude smaller in terms of number of parameters. Furthermore, when we add sampling, a method where we sample the action space of each of the agents for different viable trajectories and ultimately select the best one, we find that our method outperforms the attention model when evaluated over 2,000 sampled trajectories. We next sought to evaluate the generalizability of our model. We did this by first changing how the mapping failure distribution was represented and found that regardless of the distribution, as long as there's a decent degree of stochasticity, our model outperformed the state-of-the-art best practices, again represented by LKH3. It should be noted that all evaluations were performed on the same model, trained over a uniform 1-to-3 distribution. We finally verified a few more things about our model. Firstly, we determined that agents trained with reinforcement learning scaled slightly better than agents trained with imitation learning. We also determined that the runtime of our algorithm scaled much better than the current state-of-the-art. This suggests that we could feasibly run our algorithm online. We also finally determined that increasing the number of iterations in the value iteration module, even after training, can provide an increase in performance. We believe that this can be attributed to the stored information in the latent features of the node encodings. In conclusion, we propose a novel approach to performing online routing of a swarm of agents in a realistic domain where dynamic challenges are present. By making use of value iteration transitions and an attention-based communication protocol, our model is able to outperform the state-of-the-art on real map graphs. Furthermore, it is able to do so in a scalable manner. Note that our novel attention-based graph encoder and scalable communication method can be directly applied in fields from ride-sharing to drone fleet management, and as such has the potential to be extended into far more into the future. For now, though, thank you very much for attending the presentation, and here's the final visualization of our model at work.
This work will be visualized on 2,426th Street in Chicago with a fleet of 20 agents. On the left, you see the lasting vehicle trails as they traverse the city, and on the right, their immediate positions. The bright dots at the top of the screen represent the ending and starting locations of the vehicles.